Weather Channel meteorologist Mike Seidel.
It's chilly outside, huh?
Tonight in Duluth, Minnesota. Hey, Mike, good evening.
Hey, Brian, another wild day here on the shores of Lake Superior. 20 inches of snow so far, 45-mile-an-hour wind gusts. We'll get a few more inches tonight and winds down, and then it's into the...
This might be related to your final.
All of Montana, sub-zero cold, wind chills at 30 below zero, only 9 in Minneapolis, St. Paul, and then on Friday it's even colder. Frigid Fargo only gets up to 5 below zero. This Arctic air is on the move, follows a blue blob. Temperatures nosediving, near 80 today in Dallas. Nearly 50 degrees colder Friday afternoon. This cold air will undercut the Gulf moisture. It's the perfect setup for ice. And we've got ice issues. And this will lead to tree and power line damage in that blue shaded area. This includes Dallas, Memphis, and Little Rock. This could mean power could be out for at least several days. And Brian, it's going to stay very cold for the season into early next week. Not a good time to lose your power and your heat. Also, there will be widespread travel impacts going into Friday and Saturday in the Deep South.
All right, Mike, we'll keep an eye on it. Mike Seidel in snowy Minnesota tonight. Mike, thanks.
When a technology company with a vision turns to Goldman Sachs for financing.
Obviously, most of the country suffering very chilly weather, including Orange County, a little bit, you know. So, some people might argue that, you know, today's cold, climate change is not real. What is your response should be? Anybody? Climate is. Anybody? Think about it for your final. So day-to-day weather change is not really climate, right? Climate is long-term statistics of the weather. So temperature change of the average. So day-to-day variation can change, but climate is average of the long times the weather. So when you're talking about the climate change, then climate change, so it is not really about, you know, tomorrow is going to be warm all the time. It's more like average over the time, okay? So that's the idea. So also, for, how many of you watched the C-SPAN? Not many, huh?
But people talk about cap and tax and they aren't sure exactly what we're talking about. Let's get back to step one. What is the problem? Why do we have to have this tax in the first place? It's about carbon dioxide. Well, what is carbon dioxide? Let's just go to a fundamental question. Carbon dioxide, Mr. Speaker, is a natural byproduct of nature. Carbon dioxide is natural. It occurs in Earth. It is a part of the regular life cycle of Earth. In fact, life on planet Earth can't even exist without carbon dioxide. So necessary is it to human life, to animal life, to plant life, to the oceans, to the vegetation that's on the earth, to the fowl that flies in the air. We need to have carbon dioxide as a part of the fundamental life cycle of Earth. As a matter of fact, carbon dioxide is portrayed as harmful, but there isn't even one study that can be produced that shows that carbon dioxide is a harmful gas. There isn't one such study because carbon dioxide is not a harmful gas, it is a harmless gas. Carbon dioxide is natural, it is not harmful, it is a part of Earth's life cycle. And yet we're being told that we have to reduce this natural substance and reduce the American standard of living to create an arbitrary reduction in something that is naturally occurring in the earth. Well, we're told the crux of this problem is human activity. It's humans that are creating more carbon dioxide. Is that true or is that false? Well, carbon dioxide is a natural part of Earth's atmosphere, but carbon dioxide is perhaps 3% of the total atmosphere that's in the Earth. So if you take a pie chart and you have all of Earth's atmosphere, carbon dioxide is perhaps 3% of that total. What part of human activity creates carbon dioxide? If carbon dioxide is a negligible gas and it's only 3% of Earth's atmosphere, what part is human activity? Human activity contributes perhaps 3% of the 3%. In other words, human activity is maybe 3% contributing to the 3% of carbon dioxide that's in Earth's atmosphere. It's so negligible, it's a fraction of a fraction of a fraction of a percent. It can hardly be quantified.
My good friend, the gentle lady from Minnesota, doesn't think there are any problems with the concentration of carbon dioxide in the atmosphere. It's interesting to listen to her say that something that was naturally occurring simply couldn't be harmful, ignoring the fact that we have the highest concentrations of carbon dioxide in the atmosphere for 2/3 of a million years. The consensus of the scientific community, not people making things up on the floor of the House, is that this has been profoundly influenced by human activity, starting with the dawn of the Industrial Revolution, where we started consuming huge quantities of coal, burning fossil fuels, accelerating that over time. The consensus of the scientific community is that this is, in fact, a serious problem.
So this is actually my first time to not to fall asleep after watching C-SPAN, after 2 minutes actually. So there was one question I was asking about whether CO2 is air pollutant or not for the midterm, right? So you had various opinions. So we didn't actually grade it based on your opinion. We did not actually grade it based on your opinion, which means that regardless of whatever your opinion is, we just grade it based on your logical thinking. Okay? We may ask you again the same question, whether you're still thinking about CO2 is not air pollutant or CO2 is air pollutant. So think about it. So again, at this time, for the final, we are not grade your answer based on your opinion. Rather, we will grade based on your logical thinking. So you can have either opinion, Michelle Bachmann's opinion or some other congressman's opinion out there. So there's two things that I need to talk about before the class. So let's dive into this review slides. So actually, this is a little different than what I uploaded. Actually, I just got rid of a couple of slides from what I uploaded yesterday, which means that if you don't see the slides that you have right now from today's lecture, which means that that's not going to be on your final. Okay? So, this is air pollution class, so I want you to remember the definition of the air pollution. And there are 3 points actually you need to remember. The first thing is that it should be human-made particle or gases, right? Particle and gases or gas. Particle. So you got to mention about both of them. So gas and particle, rather than just one, right? And then it should be highly built up in terms of concentration, and then it should affect on human life, right? There's 3 components in their definition of air pollution. Why this is not working? Let's go for here. Okay. So again, there will be one calculation question this time. So if there's a calculation question, then there will be an equation will be provided, right? So think about that mixing ratio and temperature, things like that. But if we put any calculation question on final, So the equation will be provided, all right? So that's the thing. And then the black body radiation, the thing you need to remember is that basically anything, so one parameter that determines energy emission from black body is just temperature, okay? You don't need to know anything else, just temperature. And then another thing is higher temperature obviously means higher energy, right? So that's the one thing. And then in terms of electromagnetic radiation, shorter wavelengths means higher energy. So three things, okay, for this thing. And then we talked about three different electromagnetic wavelengths region, right? One is UV, shortest one, which is highest energy. And then visible, somewhere between 400 nanometer to 700 nanometer. And then IR, which is sensible heat, which is longer than visible. So one thing I want you to remember is at least visible wavelengths region is somewhere between 400 to 700 nanometer. Just remember that numbers in your head. So that's the thing. And then another thing is that sun is mostly emitting visible, right? Earth is mostly emitting IR. So that's, we talked about this thing over and over and over again, right? And then, yeah, that's it. That's all you need to know. And there's two kinds of ozone out there, right? Again, the one ozone on the surface is produced by what? NOx, CO, VOCs, right? Chemical reaction, photochemical ozone production over the surface. And then we don't want to have high ozone concentration on the surface, but we want to have high ozone concentration in the stratosphere because it's going to filter this thing away, right? So we talked about it. So the plot out here, basically, Earth's history about 4.5 billion years. It is pretty recent thing that we have oxygen about 500 million years ago. Finally, Earth has a composition that we have right now, and then only past 200 years, we just messed up the composition of the Earth, and then we just caused a lot of air pollution problems. So that's the whole theme of this class, right? So the pressure is not constant over the altitude, right? So pressure is changing over the altitude, and then pressure is decreasing very fastly, right? Over the altitude. We call it exponential decay. And then there was one question about why EPA enforcing mixing ratio rather than number of molecules in the midterm, right? So the correct answer is pressure is changing as a function of altitude. But many cities in the U.S., for example, Denver is located 1.6 kilometer. So the number of gas molecule is only 80% of what Irvine has. So to compare apple to apple, you gotta compare the mixing ratio rather than number density. So that's why EPA enforced the air pollution concentration with mixing ratio, not number density. So that was the answer for that. A lot of you confused by that, so that's the answer for that. And then here is the composition of gases in the atmosphere. Again, nitrogen and oxygen is mostly composes the air, so almost 100%, almost 99%, right? And then a lot of inert gases is composed rest of them. And then if you add these things, a percentage is 99%, 96. So that's almost 100, right? So all these things are not even air pollutants, right? So concentration of air pollutants are extremely small. For example, CO2 is 380 ppm. So the Congresswoman Bachmann's statement about 3% of CO2 is completely wrong statement. So 380 ppm is about 0.3%, right? ppm parts per million. Yeah, 0.3%. So although so CO2 is a very, very tiny fraction, that's right statement. But so all the air pollutants is the same way. It's very tiny fraction of the air composition, but still it can affect our life. And then it can affect on the, kind of art forms outside, and then the plants, and then animals. So that's the one thing I want you to remember about this air pollution thing. So, the air pollutants compose this very small fraction of the air, okay? So in terms of concentration. So this is the, we use these things a lot during the midterm, and then especially for beginning of the class. So again, if I ask this thing in your final, we'll provide this equation, so which means that you don't need to remember this thing, okay? So talked about CO2. So we talked about a number of things that excess amount of CO2 can cause in our system. The one thing we talked about was ocean acidification, right? So actually one student came to my office, and then we talked about this slide. And then, the student was kind of freaked out. And then, should I remember this whole thing? No, you don't need to remember this whole thing. So main punchline of this slide is that, so if you are a chemist, then you can understand this chemical reaction. But take a look at this reaction. Basically, if you have very high CO2 concentration, or if you just CO2 concentration in the atmosphere keeps increasing, what's going to be happening is that more CO2 is going to be dissolved into the seawater, right? And then produce H+. So if you have more H+, that means what? Anybody? Can you hear something? Go for it.
More acidic.
Yeah, it's going to be acidic, right? So basically, if there's too much CO2 in the atmosphere, then your seawater may get acidic. And then we watched that video clip about ocean acidification. So a lot of shellfish, so shell basically composed by calcium carbonate, and then it can be very easily dissolved by the acidic water, right? So that's why there's the shellfish crop yield got decreased, especially in the near Seattle area. So that was the one side effect of the CO2. Concentration increase other than global warming, right? So we talked about this thing. Again, 6 air pollutant, that's basic thing. You gotta remember this thing. And then we talked about 2 things, right? So London type smog, and then that's the other thing, LA type smog. So London type smog, mostly caused by coal burning. And then if you take a look at this molecular structure, very, complicated one, but it's basically composed by carbon, hydrogen, oxygen, and sulfur, right? So what you expect coming from this molecular structure when coal is burned is basically, what is this thing? We talked about, obviously CO2, right? And CO in complete combustion, and SO2, right? There was one more thing we talked about. Anybody? Soot. So this is coal burning, and then that's a steam engine, right? So that actually caused that London type smog, right? So we talked about this thing, and then internal combustion engine. Basically, each car has one of these things, and then if you take a look at the gasoline, there's no sulfur in the structure. If you take a look at this, so you expect to come out. You can expect to that this internal combustion engine emits CO, CO2, but probably not SO2. And then coal is kind of a solid material and a black thing. So once it got burned, so black carbon can be coming out. But so soot can be coming out, but gasoline is liquid, it's clear, so this thing emits far less soot, almost nothing in terms of soot. So, and then it is emitting CO and CO2, and then another very important important air pollutant is NOx, right? Basically, temperature inside of the internal combustion engine is very high. So the very stable, although it's very stable in terms of the chemical stability, N2 and oxygen are very stable, but temperature gets very high. So the bonding can get broken and then produce NO from N2, atmospheric N2, and then O2. Okay, talked about this thing. So 3 air pollutants coming out from internal combustion engine: NOx, CO, and CO2, right? But it depends on whether you think the CO2 is air pollutant or not. So that's your decision. So, so this is the internal combustion engine that each car has, and then this is the steam engine. And then at this time, I don't expect for you to remember all those arrows and then arrows direction. Okay, I will make your life a little bit easier. Basically, what you need to remember is ozone on the surface is produced by the NOx, right? NO and NO2. And then VOCs and CO, right? Reactive organic compounds, right? Reactive organic gases, ROGs. So you don't need to remember this whole reaction mechanism, but just remember NOx, CO, and reactive organic gases or volatile organic compounds produce ozone at the surface. Okay? That's one thing you need to remember. So at least in the US, especially in the in Los Angeles area, metropolitan area, we decreased the ozone concentration quite a bit, past about 30 years. The reason behind of it is that we knocked down the NOx emission, NOx concentration, and VOC concentration, which means that we are getting lower ozone concentration. So this is basic idea. But again, we talked about that it's kind of a very complicated chemical system, produce ozone from NOx and VOCs. So there's some non-linearity exists in the ozone chemical system, which means that if you just knock down the NOx from the city, that may actually increase the ozone because of non-linearity. But that may be a little too much for some of you guys, so you don't need to remember that thing. But if you understand the chemistry, that's one thing you need to remember. I want you to remember, but that won't actually, that won't be in final. I won't ask you about that. So basically, punchline is that NOx, VOCs, and then sunlight, right? That's very important ingredient for the Los Angeles type smog, producing ozone in the surface. So usually photochemical ozone smog issue is happening during summertime, right? But on the other hand, what did we talk about? The London type smog is usually happens when? Wintertime, right? Why is that? Inversion, right? We talked about it. So that's the thing you need to remember. So previous discussion is all about gas phase chemistry, but a lot of air pollutants. So we talked about air pollutants are either gas and particle. So we talked about a little bit of a particle. One class, actually, Ian gave a lecture about this, right? So the particle as air pollutant we are worrying about is the mass size range is about 0.1 micrometer to about 10 micrometer. So 1 meter is about length of this much. 1 yard is about 1 meter actually. So micro is 10 to minus 6. So if you imagine this, length of thing, and then if you chop these things out million times, then that's basically 1 micrometer. So it's very, very tiny particle. But still, that can affect our health, right? So we call it small particle. It's somewhere between below the 0.1 micrometer, and the medium particle is 0.1 to 2.5. Large particle is 2.5 micrometer or higher. So probably the number you want to remember is about 2.5. So 2.5 micrometer is kind of borderline between smaller particle and large particle. And then we talked about this thing, why the particle size matter. I didn't include that slide here, but usually 2.5 micrometer particle gets all the way into your lung tissue, right? Then it's gonna stick in your lung tissue and it's not gonna be coming out. So that's why we are worrying about that 2.5 micrometer, all right? So we talked about it. And then the other thing, the misconception that people have is that particle, it's going to be just staying in the atmosphere as it is. But that's completely wrong. Particle is very dynamic, which means that particles are growing, right? That's one thing you need to remember. How it can grow is particle-particle interaction or particle-gas interaction, and then gas-gas interaction actually make a very small particle, and then it grows to the larger particle, then eventually that removed from the atmosphere, because it gets heavier, then it will be just settling down, right? Gravity starts to walk from that time point. So we talked about this thing. So basically, extremely small particle, for example, particle size diameter smaller than 0.02 micrometer, which is 20 nanometer. So it takes about 228 years to fall just 1 kilometer of altitude, which means that if we have this kind of a size, very small particle in the atmosphere, then it will stay very long time in the atmosphere, right? But the time to fall is decreasing dramatically as a particle grows. So if the particle size gets about 10 micrometer, it takes about 3.6 days, right? So once it gets a large particle, it will be settling down to the ground. So the consequences of the aerosol growing is basically it will be removed from the atmosphere, right? So that's the thing you need to remember. So we talked about 6 different sources of the aerosol, and then green is natural completely, right? Biomass burning can be either natural or anthropogenic. If the biomass burning is caused by the human activity, there can be air pollution. But if it is natural, such as lightning, things like that, then it is an anthropogenic thing, so we can call it a pollution issue if the particle coming from this biomass burning cause any problem in your life. And then fossil fuel combustion and then industrial activities, if industrial activities are emitting any particle, that means that this is air pollution, right? So depends on the sources. We can call it pollution or just natural phenomenon, right? So we talked about it. This is again about the all the different processes, specific processes, how aerosol is growing. So what you need to remember is basically dry deposition, sedimentation, rainout, and washout. So sedimentation and dry deposition is the same thing. Basically, a particle just dropped from the atmosphere to the ground. And then rainout, washout is basically the same thing. Once it gets rain, and the particle gets removed from the atmosphere. And then particle, I mentioned about that particle is actually growing, and that there are a number of processes that grows the particle in the atmosphere. And then coagulation, nucleation is actually gas and gas is kind of binding together. This is starting point that actually gas molecules makes particle in the atmosphere. So we talked about this thing. This is cartoon to explain that aerosol dynamics in the atmosphere. And then what is this thing? This is thing again. So basically, again, so this thing and this thing is the same thing that a lot of people, even some scientists, think that aerosol is just stay in the atmosphere and then it just stay there as it is, and then think that aerosol is very boring thing. But in the atmosphere, that a lot of chemical reaction is happening, change their constitution, chemical characteristics of aerosol, and then it's growing. So physical characteristic of aerosol is changing as time going by. And then it can be settling down to the ground, but also this aerosol particle become a cloud seed. So basically to make the cloud, and then to make rain, you need aerosol particle in the atmosphere. So we talked about this thing. And then we talked about this thing, how there's health impacts of the particle. So most of the lung is related with the lung that particle effects on the health. And we moved on to the, what's it call it, meteorology after that. So we talked about two kinds of winds during the discussion. One is geostrophic wind, right? So remember this thing, right? High pressure. So the pressure gradient, right? That's one thing. Pressure gradient is initiating wind from high pressure to low pressure side, right? Then once air is moving, Earth is rotating, what's kicking in? What kind of force is kicking in? Coriolis force is kicking in. If it is northern hemisphere, what's the direction? Right side, right? So it's going to be, right? And then because it is rotating, so centrifugal and centrifugal force is also balance things out like this. So there are three kinds of forces, right? Effect on geostrophic wind, right? Which means that the wind's up high, right? Something like 2 kilometers above from the surface. So that's three forces determines the wind direction over the Earth, right? But surface wind, there's one more forces, right? What was that thing? Friction, right? So, so this is geostrophic wind. Then let's go for red for the friction. So due to friction, it is moving away from the high pressure to low pressure side due to friction. So also the other thing we mentioned about was that usually in low pressure system, there's upwelling because on the surface, right, air is moving in. So air is moving into the surface, so some of the air molecules should go somewhere. Where it goes, it's just going up, which means that upwelling thing going on. So condensation is happening. So usually in the low pressure system region, then there's a more wind, and then precipitation cause less air pollution, right? But usually high pressure system, air is moving out from the high pressure center, and then air gets subsidized. So a lot of air pollutants got trapped over the surface, so air pollution problem gets worse in high pressure system. So we talked about the London smoke, and then we watched several video clips that's the hazy issue over the mega city in China. It's all associated with the high pressure system. Yes, so this is the region behind of it, right? So this is the surface wind, right? So same thing. And then, so in global scale, the implication of this thing. So this is a regional scale implication about high pressure and low pressure system. But in global scale, this air movement, the implication of this horizontal air movement is that it takes about 2 weeks to air actually moving around the world. That means that basically air pollution from eastern part of the US actually can be transported over the Europe, right? The air pollution in Asia can be transported over the US. So so air pollution can be international issue due to this kind of a relatively very fast air motion in west to east side, okay? And then it takes a relatively long time to mix between northern hemisphere and southern hemisphere. It takes about a year. And that means that if if air pollutants chemical lifetime is shorter than 1 year, much shorter than 1 year, there's no chance that a lot of usually human activities are emitting the air pollutants to the atmosphere. So not much of the those kind of pollutants will be transported down to the southern hemisphere because it takes such a long time from mixing between the northern hemisphere and southern hemisphere, right? So that's one thing, and that's horizontal air movement. Now, if you take a look at the vertical air movement, we talked about boundary layer, which is the surface layer below this inversion layer right here, right? So this inversion basically kind of traps. So this is kind of blocking the air movement from the boundary layer and the free troposphere. So that's usually happening somewhere between 0.5 to 1 kilometer. So basically, the emission is happening over the surface. So that's not going to be easily mixed up between under this mixing the mixed layer, what we call it boundary layer, and then up here, right? So if this base altitude is lower, that means that if there's the same amount of the air pollutants are emitted to the atmosphere, then the concentration will get higher because basically you have small container to to deal with, to mix with that your air pollutant emission from the surface, okay? And then again, this is another thing that you need to consider, that the cause of that London type smog and then all those smog problem that we watched the news clips in Chinese mega cities. It's that usually winter time, we have relatively shallow mixing depth that cause higher concentration of the most of air pollutants, and then that cause that those kind of London type smog out there, make it even worse, right? Talked about it, so this is also time scale that you don't really need to remember all this time scale, but you at least got some idea. So if you see this kind of a diagram, and then if you take a look at lifetime of chemicals, for example, CFCs, right? CFC's lifetime is about 4,200 years. We talked about it. So CFC once emitted from the surface. So this CFC can be transported from troposphere to stratosphere, you think? Yes or no? Yes, because it's long lifetime. So it will just live long in the troposphere, so it will eventually go up to stratosphere, right? How about NOx? NO and NO2 has maybe one day of a lifetime. You think the NOx that emitted from the surface can get into the stratosphere? No, there's no chance. But we talked about this thing, N2O. I don't have good number on top of my head, but it's well over lifetime is 5 to 10 years. Then N2O can get into the stratosphere? Yes, right? So this N2O can get into the stratosphere, it produces NOx in the stratosphere, and then that destroys the ozone in the stratosphere. We talked about it. We will discuss about it. So that's the thing that you need to remember, kind of related this mixing time scale and then chemical lifetime of the air pollutants, and then how those air pollutants is going to behave or distribute it over the atmosphere. That's something you need to remember. Kind of critical thinking skill rather than just remember these numbers. Okay? So that's the thing. So after that, we talked about visibility, right? So now, so you got to remember again about this thing, right? So basically, about UV wavelength region is below about 400 nanometer. Visible again between 400 to 700, right? And UV is kind of 5 to 50 micrometer region. We talked about it. And then there's an interaction between gas and particle, right? And then each gas and particle can interact with the visible wavelength region. And then two kind of things out there. What is that? Two things. Both starts with S. Not S. One is A, one is S. Absorption and scattering, right? So there's four kind of things out there. The interaction between air pollutants. Air pollutants can be either gas and particle, right? So gas can absorb visible wavelength region, and then gas can scatter visible wavelength region, right? And then aerosol particle can absorb visible wavelength region, then a particle can scatter a visible wavelength region. So 4 kind of things. That's something you need to remember. So why this thing is here? So basically that visible wavelength region and UV mostly happening the electronic transition, basically a bond breaking. And then this thing is something you need to remember to understand climate change, global warming. So basically greenhouse gases that we know of is that the specific interaction between that IR and the gas molecule is vibration, right? Vibrational transition. So basically this particular wavelength range, IR, can actually vibrate molecule. And then what kind of vibration can absorb the IR is the asymmetric vibration. So for example, CO2 can make the asymmetric vibration, like if this thing is moving like this. So that's kind of asymmetric vibration, what they call it. But if you think about CO, is that triple bond and double bond? It should be triple bond, right? So this thing couldn't make this asymmetric vibration. So CO is not greenhouse gases, but CO2 is greenhouse gases. Okay, that's the what greenhouse gases, okay? How, what's the interaction between the gas molecules and this vibrational transition. So if you are not really familiar with this thing, so what you need to remember is that the IR, actually interaction between IR and gas molecule makes a vibrational transition, and the gas molecule that can be absorbed this IR is what we call it greenhouse gases. And then in the atmosphere, most important greenhouse gases, CO2, 2 more. What are the 2 more important greenhouse gases? Methane and N2O. Yeah, 3 things, right? And then CO is not greenhouse gas, okay? Oxygen is not greenhouse gas. Nitrogen is not greenhouse gas. So if molecular oxygen is greenhouse gas, then we are in trouble, right? It's 20%, right? And nitrogen is greenhouse gas. Again, we are in trouble, but thankfully, they are not greenhouse gas. Okay. So absorption of a particle. One thing we talked about discussed about several times is that soot can absorb visible wavelength region, and then it's black. Basically, it absorbs everything in terms of visible wavelength region. Then it emits IR, so this black carbon soot is warming up the atmosphere. So that's one thing we talked about it. So we a little bit struggled about this thing. So based on this, what's the most important interaction between visible wavelengths and gas and then particle to determine visibility? Scattering, which scattering? Particle scattering. So that's one thing you gotta remember, okay? So we talked about this thing, why in the summertime, Los Angeles region has bad visibility, and then why wintertime, Central Valley region has bad visibility. So Central Valley region has inversion because it's valley, there's inversion going on. So a lot of air pollutants get trapped inside the valley. So that's why in the wintertime, Central Valley, California has horrible air pollution problem. And then Los Angeles region, there's LA type smog, photochemical smog is going on that needs sunlight. And then it gets worse in the Los Angeles basin. So that's why Los Angeles basin suffers visibility problem during the summertime, all right? So we talked about air pollutants control technology. So one thing is catalytic converter, right? So you need to understand a little bit of chemistry. Something can be useful for your life if you understand this thing. So we talked about we don't want to have too much of CO2, VOCs, and NOx in the atmosphere, which cause ozone formation problem. So we want to make one CO and VOCs. So basically this is organic compounds which composed by carbon and hydrogen, right? And then NO2. So what this catalytic converter is doing, that every car has this thing, putting a lot of heat and then make complete combustion and then convert this thing CO to what? What? CO2, right? If we're burning completely hydrocarbon, it's going to be CO2 and H2O, right? If you burn this thing again completely, N2 and O2. So N2 and O2 is good. Basically 99% of the atmosphere is nitrogen and oxygen. But basically this catalytic converter is great in terms of removing CO, VOCs, and NOx from the atmosphere. But still, there's CO2 is coming out. So again, it depends on how you define it. CO2 is air pollutants or not air pollutant. That's your decision. But CO2 cannot be removed by catalytic converter. Okay? That's one thing you need to remember. So we talked about this thing. So they basically, this one book actually catalyzed to make the big movement on the environment, and then EPA is formed in late 60s, and then start make the some law to control the air pollution problem, and then the law is Clean Air Act, and the still Clean Air Act is actually kind of regulating air pollution problem. There's several iterations as time passing by to deal with the upcoming air pollution problem as time going by. Any questions? Nope, clear, right? So we talked about catalysts, so CO converts CO2, and then oxygen N2, and then hydrocarbon eventually converted everything into basically CO2, water, and then N2 and O2. That's what catalytic converter is doing, okay? And then there's a bunch of numbers in this chart. One thing that I want you to remember, at least, is the ozone level. So 8 hour in national standard is 75 ppb. So it's 0.075 ppm. So in ppb, it's 75 ppb, right? Actually, California is 70, but it's more strict, even more strict than the federal level. But federal regulation level is 75 ppb. All right. So radon. So that's one thing that we talked about, indoor air quality issue. Usually California, the radon is not the big problem, but if you just move into a place like Colorado, place like that, some part of the country, radon is a problem. Why radon is a problem? Radon is gas, so it can smear into your house, and then once it gets into the lungs, so where's the radon? Radon is right here, and then in 3.8 days, it will become polonium. Yeah, it sounds pretty dangerous, right? So basically, this can be accumulated in your lung, like lead can be accumulated in your lung. So it takes us 3.8 days. So if there's 100 molecules of radon in the room in 3.8 days, so half of them is going to be formed as a polonium, changed as a polonium by emitting the alpha particle. So this is energetic particle. So once this alpha particle kind of hit your lung tissue, that's obviously bad for your health, and then it just keeps changing, and then it's emitting energetic particle, alpha particle, and beta particle. So that's the problem. So this the the region that has a high radon concentration is mostly Rocky Mountain region, and that's one thing we talked about radon. And then one other thing we talked about is asbestos, right? So asbestos, the size of it is about somewhere between 1 to 10 micrometer, and then it's needle shaped. So once it gets into your lung tissue, it's not going to be coming out. So that's bad for your lung health. So again, this thing again. So basically, the size range, the size of this asbestos is the perfect size range that can get all the way down to your lung tissue. So that's why it is harmful for your lung health. So as asbestos has been used in many different things, mostly insulation. So what's the major health concerns due to asbestos? One is lung cancer, one is mesothelioma, right? That's kind of things you want to remember. Prepare your final. And then another thing, so we talked a lot of EPA. So EPA basically controlling outside air pollution, right? So ambient air pollution. But inside, especially workplace, the air pollution issue of the workplace is not governed by EPA, it's governed by OSHA. So OSHA is Occupational Safety and Health Administration. So if you get a job and then if you have some problem with your office air quality, things like that, you don't want to go to EPA, you want to go to OSHA. So it's a practical thing. So it's good to remember, right? And then we talked about acid rain. So we started with HCl. So basically acid rain means that rain gets acidic. So what's acidic? Basically determines by this H plus, right? So HCl can provide H plus in the water. So there's around the 3 different acids we talked about: HCl, sulfuric acid, and nitric acid we talked about. So HCl is not really a problem anymore because this LeBlanc processes got banned, and then we don't need to use this thing anymore, right? We talked about it. And acidity. So if I put this thing in final, I'm not gonna put this equation. So I'm not gonna provide this equation. This thing, one thing that you need to remember in terms of equation, it's a log scale. So we talked about this thing several times in quiz and at homework, things like that. So I think you guys remember this thing at this time point. So basically pH 7 is neutral, right? That means what? Can I get some help? Just shoot it. Yep. So you gotta at least tie these things together, right? So let's see, 10. So which side is more acidic side? Lower number or high number? Lower number, right? So this is, right? So that's, we went over this thing several times. And then modern day acid rain problem is mostly coming from sulfur. So mostly the gas phase sulfur is emitted by SO2, right? And then this SO2 is somehow converted into sulfuric acid. So the air pollutants that cause sulfuric acid rain problem is not SO2, right? It should be acid, which is sulfuric acid. Okay? So that's, you gotta know about the what's the SO2. That's emitted by the mostly coal burning processes. And then sulfuric acid is kind of made from SO2 by the chemical reaction. Then this is actually causing the acid rain problem, sulfuric acid. Okay? So things going so 25 minutes. So we talked about, especially in the Ohio River region, there's a lot of power plants that are using the coals. So if you take a look at this pH distribution in 1994, so usually acid rain is observed in the Ohio Valley region near the power plant, right? So basically power plant emits SO2, and then they are converted into sulfuric acid, and then they cause acid rain problem, okay? And then if you take a look at the improvement of the acid rain, it gets much better. So again, so in natural condition, because of CO2, rain is a little bit acidic, so about 5 to 5.5 of pH. pH is the natural rain pH. So this additional so H plus concentration is coming from this sulfuric acid. So by a technological breakthrough, basically SO2 is removed from the stack gas. So the pH, the acid rain problem gets much better these days, at least in the US. We talked about this thing. And then we moved to the ozone layer. So ozone layer in stratosphere is a good thing because it filtered out UV. We just went over this thing several times, and then we talked about Dobson units. So that's one thing. And then how ozone is made in the stratosphere. So what I expect for your final is that if I, for example, right? So this is the reaction that produces the ozone. So so can you fill this parenthesis by putting some molecule? That's something I expect from you for the final, right? So if you take a look at that, there's 1 oxygen, and then there's 3 oxygen, which means you need 2 oxygen, right? Okay? So simple math. So that's what I expect. So I don't expect for you to remember this whole thing ladder, you know, if I just something. Did I underestimate you guys? I can make it worse. This thing much more difficult. No? Fine? Okay. Okay. Let me know. Email me if I just underestimate you guys, all right? So that's the one thing I expect for you to remember. So talked about this thing. So if you can understand about the chemical reaction, then you can actually, there's 1A2, you can actually describe why the ozone concentration gets maximum between 20 to 30 kilometer. If you can do that, that's great. But if you cannot, then just remember ozone concentration gets maximum somewhere between 20 to 30 kilometer, right? So again, to understand how CFC destroy the ozone in the stratosphere, then you gotta remember lifetime of CFCs. You gotta know. So basically what you need to know is the CFC has long lifetime and it takes a long time to air pollutants actually gets into the stratosphere from the troposphere. So so CFC has a long time, so it can get into the stratosphere, right? So before we discuss about CFC, we talked about NOx. NO and NO2 can destroy ozone in the stratosphere. So NO and NO2 has very short lifetime, but it can get into the stratosphere because if the airplane, there's a lot of airplane is flying in the stratosphere and then emits directly and NOx to the stratosphere, then it can start to destroy ozone. Ozone in the stratosphere. So the scientist who won Nobel Prize to find this chemical mechanism is Paul Crutzen. Talked about this thing, and then this specific mechanism, right? So this is not really specific mechanism. So basically, specific mechanism is that NO plus ozone, NO2 plus O2, NO2 plus O is NO plus O2, right? So it can go back and then make the catalytic cycle again, something like that, right? Then you can just take a look at the balanced pseudo oxygen. So there should be 3 oxygen here, so that's ozone, right? That's something. So yeah, so when you take a look at this chemical reaction, don't get freaked out. It's just simple math, okay? Scientists is not really that smart than, as you kind of expect. We are kind of lazy, and then we are not that smart, and then you can understand everything what we are talking about if you are not get freaked out, okay? So that's the main message about this thing. So we talked about CFC, and then this chlorine is actually destroying ozone. So this is the same thing. If I just kind of skip this thing, then you can kind of should be able to guess that CLO should be here, kind of thing. Okay. And then this is a distribution of ozone, kind of yearly average from. This is the equator, minus 90 is the south pole, and then plus 90 is the north pole, right? So if you take a look at the ozone decrease, in the mid-latitude region, actually ozone decrease is not that high compared with the south pole, right? So we talked about south pole ozone hole by starting looking at this change of the ozone in the whole world, right? So why there's ozone hole over the Antarctica, over the South Pole in very short amount of time? What was the season the ozone hole is found? Spring, early spring, their spring, which is about October, late September to October to maybe late October time frame. So there's a couple of things you need to remember. One is, so let's start from here. You need to remember it's the vortex, right? That isolate the air over the Antarctica. And this ice particle, right? Because it gets really, really cold. So ice particle observed some of the chemical species and produced a lot of Cl2 and then ClNO2. And then once sun came up, then just a lot of ozone production is going on. So that's one thing. So you can just take a look at this thing. It's not here, because I think I include one kind of a time series of the ice particle distribution, and then sunlight, and then CLO, and the CL, things like that. So basically, what you need to remember is the ozone hole phenomenon is very short, about a month time frame. It just happens just a month, right? And what else? And then it caused by vortex, something you need to remember is a vortex, and then very low temperature, make the very special ice particle, and then they can produce a lot of chlorine precursors that can produce Cl and ClO when sun come up. So once springtime came, it just sun is start to come up, right? During the winter time, there's no sun over the Antarctica, so sun is producing chlorine, and then basically making this reaction. So that's why ozone is completely go away during the early springtime over the Antarctica. So that's the thing that you need to remember for the ozone. Okay, so we briefly talked about this thing. So in the Arctic, we haven't seen any ozone hole past 10 or 20 years because Arctic stratosphere is relatively warmer than the Antarctic stratosphere. But we talked about that actually troposphere gets warmer, some place should gets cooler. So Arctic stratosphere gets cooler, so we start seeing this ozone hole over the Arctic region because stratosphere gets cooler. Finally, that ice particle, that special ice particle that can create a lot of chlorine compound in the stratosphere, that chemical reaction start to kick in. Okay, that was the one thing. So we shifted the gear to our final topic, to climate change. So we discussed about what's the cause. Basically, we discussed the whole discussion what's the cause of this recent temperature increase past about 200 years, right? So there's natural fluctuation of temperature. There's a lot of things that cause the natural fluctuation of the temperature, but we did not discuss about the natural causes, but mostly we talked about the greenhouse gases. So in natural condition, greenhouse effect is actually very helpful thing to maintain life over the Earth, because if there's no greenhouse gases in the atmosphere, if there's no atmosphere in the atmosphere, no gases in the atmosphere, yeah, that's correct. Right. It's tongue twisting. So then temperature is going to be much, much lower. It's below the freezing point, right? We talked about it. But thanks to this natural concentration of right amount of, let's say, right amount of the greenhouse gases, temperature actually maintains above than the freezing point. So there's life can exist over the Earth. So we talked about that thing. But the problem is that this bivibrational transition of these greenhouse gases like CO2, methane, and N2O is blocking, basically observing the Earth's radiation that caused the global warming. So we talked about this thing. But so there's a couple of uncertainty associated with this global warming. We talked about this thing, but before then, we talked about these scientists who firstly postulate that human-made CO2 can actually increase the temperature over the atmosphere. So his name is Arrhenius. So that's the good name to remember, I guess. So we talked about that, then Earth's climate system. So basically, this is all about energy balance. We talked about it. So there's the energy is coming from the Earth, from the sun. So Earth is not really emitting energy by itself. So sun is producing energy by nuclear fusion, right? We talked about this thing very beginning of the class. So the energy is coming from the sun, and then some of them are reflected away. We call it the ratio between total energy and then the energy that reflected away from the Earth as albedo, right? We talked about it, albedo, and then that's one of your homework question. And then quite a lot of fraction is about 70% got absorbed by the Earth, and then it's emitting because it is black body. The energy absorbed by the Earth is emitted by the Earth too. But most of the energy is in form of the visible wavelength region, but Earth is emitting IR, and the IR got trapped by greenhouse gases in the atmosphere, and then re-emitting those IR into the Earth again. That's by definition greenhouse effect, right? So right now the concern is that we are increasing too much greenhouse gases. There's more energy is from the Earth is absorbed by the atmosphere and then re-emitted to the atmosphere. So we take a look at the other planet. So obviously Venus, mostly by the CO2, and then there's a lot of gas molecule in the Venus atmosphere. Is surface pressure is 90 bars compared to the Earth is just 1. So there's 90 times more gas molecule in Venus atmosphere. So that causes a lot of greenhouse gas, greenhouse effect. So the equilibrium temperature, if there's no atmosphere over the Venus, then temperature is going to be 252. But due to greenhouse effect, temperature gets 730. So that's one thing we discussed about. And then this is the thing that we talked about. Although, you know, a lot of parts, most of the part of our country suffer very cold weather right now. So we had a seminar speaker actually, one from the Denver yesterday, and she said Denver's temperature gets like 7 Fahrenheit at this time point. So, so some people may complain about, you know, it gets cold today, so there's no climate change thing is going on. It's complete hoax. But it's about statistics, not about day-to-day variation of the temperature. Okay? Again, I just want to stress on that thing, right? The same slide here. The concern is that this CO2 is most powerful greenhouse gases in terms of concentration, because we have so much CO2 high CO2 concentration in the atmosphere. But by molecule, N2 is more powerful greenhouse gas. We talked about this thing. So basically, the problem is that bringing this fossil fuel to the atmosphere in forms of CO2. So renewable energy means that basically using the CO2 in the atmosphere and then that recycling of CO2 in the atmosphere, or just bringing a completely different form of the energy source that wouldn't bring this fossil fuel carbon into the atmosphere in forms of CO2. So that's the definition of the renewable energy at this time point we have, at least. So we talked about CO2, methane, and N2 so many times. But one uncertainty, there's many uncertainties in climate change. There's one uncertainty we talked about is role of aerosol, especially cloud. And then you read one of the article about it. So basically cloud, it depends on where it's located, right? It can warm up the Earth's surface, or it can cool down the Earth's surface too, right? So what is the cloud that cool down the Earth's surface? It's the low cloud, right? It basically reflects a lot of sunlight away, so less energy gets into the Earth, so it's going to be cooling down the Earth's surface, right? But a cloud up high, we call it cirrus cloud. That's something, you know, good name to remember, cirrus cloud, actually increasing the temperature of the Earth. So the New York Times article, there's scientists at MIT basically claiming that once global warming gets, you know, intense due to CO2, then there will be more cloud, and then Earth is going to get cooler. So that's one. So one scientist theory. There's a lot of discussion going on. But so our most dominant view on climate change is that although we have very uncertainty still out there to predict exact in temperature increase down the road, but we are very sure about if we just keep emitting CO2 in the atmosphere, then our Earth is going to be getting warmer. So that's the scientific consensus at this time point. Obviously, there's few scientists has problem with that statement. So I introduced two scientists. One is that professor at MIT, and then the other one is Judy Corey at Georgia Tech. So there's a lot of uncertainty there. So there's some minor voices out there. So at least I think I should introduce that opinions to you, to be fair. But if you just ask hundreds of scientists out there, probably 99 scientists probably say that it gets warmer for sure. So that's the kind of current status right now in terms of understanding of the climate change. So we talked about CO2 emission, China by country emitting high CO2 to the atmosphere. But if you divide by the per capita, mostly North American country like US and Canada emits more CO2 by person, and then Saudi Arabia and Australia, European country is much lower, and Asian country is relatively lower. And then, but one concern is that the economic development in Asian country, and then there are a lot of people out there may increase CO2 very fast pace. So that's the concern. So we talked about this Kyoto Protocol. So basically, we talked about two different protocols out here. Kyoto Protocol is about CO2. So this is still kind of limbo right now, but Montreal Protocol is big success to stop kind of banning the CFC, right? So there are two protocols out there. One is Kyoto, it's about CO2, and then Montreal is CFCs. We talked about this thing. So you can just, for this thing, just take a look at this question and then find out whether you can answer this question, right? That's the good way to prepare your final. Then if you cannot answer your question, these questions, then go back to that PDF file that I mailed you, and then read this thing. It's only just 1 page long or something like that. And then we talked about this extreme weather events. So we are talking about heat wave, droughts, and floods, and hurricanes. It's likely increase the intensity and then number of frequencies due to climate change, global warming. But one thing we are not sure, what was that thing? Tornado, right? So we talked about this thing, sea level rise, and you can take a look. And then one thing that people claim, other than cloud uncertainty, is that solar intensity change, but simply solar intensity change over the past few tens years, even if we go back to the few hundred years before, then solar intensity change cannot explain current fast warming that Earth is suffering past few hundred years. So that's one thing we talked about it. So the answer is obviously greenhouse gases. So that's the thing that we talked about. So that's the Montreal Protocol. So the CO2, so because simply CO2 has the highest concentration, CO2 is a problem, but if you just take a look at molecule by molecule, if there's same concentration of these greenhouse gases in the atmosphere, then N2O is going to be the biggest problem, simply. But N2O has low concentration at this time point in the atmosphere. So overall, if you factor in the concentration of these greenhouse gases, CO2 is the biggest problem. So how certain we are in terms of future prediction, usually climate model is doing good job in terms of predicting the Earth's climate in normal condition. But we talked about, so this is one of the result of the climate model. Actually, climate model actually predict reasonably the temperature increase over multiple different continents. And then these things are all caused by the anthropogenic emission of greenhouse gases. And then this is, again, things like that. But one thing we discussed actually last lecture was that if this kind of ocean circulation pattern gets changed, then actually abrupt climate change may be coming. So we talked about the ice melting over the Arctic may decrease the density of the water over the North Atlantic. That may stop this thermohaline circulation of the seawater. So it takes about 1,000 years that what the seawater gets sunk in North Atlantic is going all the way to the Pacific underneath of the ocean, and then get back to the surface water, and then it's coming back to the North Atlantic. So this cycle takes about 1,000 years. But if we kind of mess up this ocean circulation, we are expecting kind of a very quick climate change is happening. So there's possibility of abrupt climate change down the road, but there's very big uncertainty associated with this abrupt climate change. So we need to control the, and then we already discussed about renewable energy. So basically renewable energy, the goal of renewable energy is that not emitting CO2 to the atmosphere, not bringing fossil fuel to the atmosphere, right? So we talked about a couple of different things. So I guess that's it for summary, but there's one thing I need to talk to you about about this class. So this is my last lecture. Again, the announcement is that I will be around the Starbucks probably 9 a.m. to noon Saturday. So come by if you have any question. So this is what couple of things not related to your final, but your life. So if I remember my college year, I forgot everything about my literature class, Chinese literature class, everything, my general education class. So probably you will forget most of these things, right? Next week, maybe even next year, things like that kind of time frame. So you may lose your knowledge much faster or slower, kind of thing, if you just plot these things out. We are scientists, we love to plot something. But, there's a couple of things I want you to not forget about this thing. One is, be a good citizen, okay? And then listen to what scientists talking to you about environment, and then warning, things like that. And then don't turn off the TV or change the channel when environmental news is coming along. Then more importantly, I think the reason behind we enforce you to science class, although you hate science or you are not that big fan of science, is that to make you a critical thinker. So science is try to make you a critical thinker. So go out there in the world, become a critical thinker, and then doubt about everything, and then think about natural phenomena in your own sense. Okay? That's my final message. And then good luck on final.